having seen the aspects of small amplitude theory, wherein the basic assumption was that the amplitude of the wave is much less compared to the wavelength, which can be most of the cases for the waves which are in deeper waters. But when the waves propagate in the coastal waters, then you cannot really have linear waves. That is, when I say linear waves, crest and the trough portion should be equal. That is, we define amplitude as equal to wave height by 2. So in the small amplitude wave theory, we say that h is equal to, so this is your h by 2, this is your h by 2. So this portion and this portion about a water level, which is either a high tide line or a mean sea level or a low tide line, this will be the about which the wave surface is oscillating. So you see that this is h by 2 and this is h by 2. Such a wave is called as a linear wave. When you want to have the linear wave, the assumption is that what we saw, that amplitude, this is amplitude, is much less than wavelength. That is, this is your wavelength. But this may not be the case, as we have already seen a number of other kinds of waves, or when I gave some of the other examples like tsunami, etc. The waves cannot be linear, and hence we resort to what is called as the finite amplitude wave theories. Small amplitude wave theory can be applied for all ranges of d by L, can be applied, there is no hard and fast rule. Small amplitude wave theory was based on the premises that the motions are sufficiently small to allow the free surface boundary condition to be linearized. Please recollect the derivation of velocity potential. What did we do? We linearized the Bernoulli equation, dou phi by dou t plus p by gamma and what we did, we used this Bernoulli equation at the free surface. When we had the free surface, this is the free surface, z equal to 0, which is free surface. Free surface is, this is the free surface, but instead of using z equal to theta, we had adopted, for simplicity, in order to simplify the problem, we adopted this for the dynamic free surface boundary condition, that is at z equal to 0, p equal to 0, and this is called as the dynamic free surface boundary condition. So from which remember we get 1 by g into dou phi by dou t at z equal to 0, for the simple reason we stated that the amplitude is small compared to the wavelength. That was the basic assumption which was made. So that is what is illustrated here. So what we have done here is, conveniently we have avoided the higher order terms. Strictly speaking, those higher order terms have to be considered, and thus we have what is called as the finite amplitude wave theories. They are quite complicated due to the relative importance of additional parameters, namely h by d and d by L. So based on the variation in d by L, Coulomb-Carpenter, sorry, it is Coulomb in 1950 he classified the waves, the wave theories as per the d by L, that is d is the water depth and L is the wavelength. So, for the entire water depth situation, that is d by L is equal to covering the entire range, you see there is a single theory which is the small amplitude Airy's theory. But for other cases, so as indicated here, you have d by L and beyond this up to this you have what is called as your Stokesian theory, and within this range we have what is called as the sinusoidal theory, and then d by L up to 1 by 50, that is less than 1 by 50, we have solitary wave. So here h by L is important, L is also important, so h by d and h by L is important, and all these things are quite important, they play their important role in defining the wave characteristics. So Airy's theory, eta by h is less than 0.5, and here you see that what is called as the Husserl's parameter. Husserl's parameter is, this is eta 0 and this is the wavelength and d is small d. So this is the Husserl's parameter. Husserl's parameter is indicated here, what should be the Husserl's parameter for the different types of waves that are being considered. For example, Stokes wave theory. So here the celerity is less than root of Gd, less than or equal to root of Gd. So here it is greater than root of Gd, that is in sinusoidal waves, and then in the case of solitary waves the speed of the wave is equal to 1.33 into root of Gd. As we have already seen the shallow water conditions, in shallow waters the celerity or the speed of the wave is root of Gd, right. So the shape of the waves are given here, so you see this is more or less sinusoidal, or it has to be sinusoidal, then we call it as Airy's theory. If the crest is slightly steeper and the trough is slightly flatter, then it enters into the Stokesian wave theories. Under Stokes wave theories you have several orders that involves that is because you have the number of orders, higher order terms you include, based on that you have the order theory. So you have the second order, third order, fourth order, fifth order Stokes theory, etc. Then we have the sinusoidal waves wherein the profile is defined by the cosine elliptical function, which we will see later. Then finally we have the solitary wave. So in the case of cosine sinusoidal waves you see the steepening of the waves, the trough is quite flat and long, and these are basically called as long waves, sinusoidal and solitary waves. The importance of sinusoidal and solitary wave theories has gained rapid importance. People are working a lot in these two waves because the tsunami characteristics can be to some extent, you cannot call it directly as a solitary wave, to a certain extent the characteristics of that of a tsunami can be represented to the characteristics of solitary waves. In the case of solitary waves you see that there is no trough. So now the waves are going to hit like this at regular intervals. So it is something like your wall of water, as we usually call in terms of as we usually a tsunami is termed as wall of water. So again I would like to reiterate that sinusoidal and Stokes solitary waves are basically shallow water waves. So let us see Stokes wave theories. Again I am just giving only the highlight of some of these theories, but you need to go through books or the references indicated in the lecture. Small amplitude Airy's theory was developed for waves of somewhat greater amplitude to be called as Stokes higher order theory, developed by Stokes in 1847. It is quite an old theory. The form was expressed as a series of terms of cos of, so you have a n standing where n equal to 0, 1, 0, 1, 2 etc. So it can go to higher numbers. Of course the waves are such waves are considered to be irrotational. In deep waters, if the terms involving h by L cubed and higher powers are neglected, then you can have a solution as given here under equation 1. As h by L, the rate of h by L increases, the crest becomes sharper and sharper, whereas the trough becomes flatter and flatter than that of a Airy's theory. So Airy's theory, you know how to calculate the C naught. How do you calculate the C naught in Airy's theory? G L naught by 2 pi, whereas here you have that additional term coming into picture. Is that clear? In Airy's theory, C naught equal to L naught by T, this is okay. Okay. So the same thing here it is represented, you have an higher order terms coming into picture. So this shows the regions of validity of various theories, and this is after Lamotte in the year 1976. The ranges of the validity of different theories, you see this is the area where you can adopt linear theory without any problem. Then this is the region where you can adopt second order theory, and this is the region where you can adopt a third order theory, and this is the region where you can adopt fourth order Stokes theory. This is the region where you can adopt your stream function theory, and sinusoidal wave theory comes in here, and this is the breaking limit. So this is the area where you have the shallow water waves, and this is the area where you have the intermediate water waves, and this is the area where you have the deep water waves. I am sure you are able to recollect the characteristics of shallow water, deep water and intermediate waters based on the displacement under the water particle displacement under different water type conditions we have seen enough. So on the y axis you have g by h by gt square, and on the x axis you have d by gt square. So this shows that the relationship between wave height, wave period as well as the water depth are the main factors that dictate which theory has to be applied for. And why are we talking about this theory, wherein you need to consider all these theories. So you know that all structures are pile structures. This is a small example. All structures are supported on piles and you need to evaluate the force exerted on this structure. Later on my lecture on wave forces or wave loads on structures, you will see that the force is going to be a function of orbital velocity and acceleration. So this is going to be a function of t, and also this u and u dot, that is particle velocities and accelerations, are going to vary with respect to along the depth. So you need a theory to describe the velocity profile for a given wave height and wave period for the pile in a particular water depth at d. So straight away, if nothing is given, you will be proceeding to calculate these two using linear theory, because it is quite simple and straightforward, without even bothering to check whether it is applicable, although it is the first step. By chance, if your parameters, that is these two parameters, are fall in this range, then there is absolutely no problem in using or in proceeding with your linear theory for calculation of the particle kinematics. Without calculating anything, you have proceeded with the Airy's theory, and then finally if one looks into the variation and your data falls somewhere in this region or somewhere in this region, now you are using a wrong theory for your data consisting of wave height, period and depth. So this is the basic step which you need to do, because you are using a linear theory in a zone where the waves are no longer linear, and in fact it is lying in the shallow water condition, shallow water situation, or maybe in the deep water situation somewhere. Here the particle kinematics, evaluation of the particle kinematics is incorrect. So you will see that u and u dot evaluation is not wrong, it is, you will still have some values, but it is not 100% correct. Now this is only in the estimation of particle velocity and acceleration. Now the force is going to be a function of velocity and acceleration, so certain degree of the degree of error involved now multiplies. So for the evaluation of the force, you will also further see that you need to look at the selection of hydrodynamic coefficients CD and Cm. These are again based on a parameter called Coulligan-Carpenter number, which is U max T by D. So here again you see the evaluation is based on this. So your error multiplies. So the first step is to make sure whether your problem falls under Airy's theory, if not under which theory, it follows, and only after getting that information proceed with the calculation of particle kinematics and then with your forces. I hope this is clear. So, expressions for wave elevation, orbital velocities, displacements, mass transport velocity, pressure, all these things based on Stokes' second order theory is provided here. Note that earlier lectures I have used A into sin theta, but purposely I am considering A into cos theta. The main reason is you should not get confused, because certain books consider A as eta as sin theta, certain books consider does not matter at all, because the properties are going to be same, but only thing is you should not keep on changing it. When I am discussing about the second order theory, I am not going to change anything. Okay. So, for the second order theory, what I am trying to do is I am considering only this portion of the wave. So, this is going to be represented in this form. This is a sine curve and this is represented by this. Is that clear? This is very important, because I see some people have some kind of problem, some of the students have some problem. So, this is very clear, I do not see any kind of confusion here. A more general expression for representing eta is given there as A square into beta b2 etc., it continues as you can see here, square cube to the power n, and also within the argument of cosine you have the factor n. So, that n takes care of the order of the wave theory that is going to be considered. So, the second order theory for the wave elevation is shown here, is given by this expression. You can simply derive, I am not going into the derivation part. For the derivation part, there are some books which do give you the details, but the procedure is as outlined in the small amplitude theory. Only thing is you need to consider the higher order terms. So, for deep water the above expression will reduce as shown here. Similarly, for the second order theory the particle velocity is given as shown here, whereas the I mean for horizontal direction and this is in the vertical direction. So, use the appropriate values for the variables concerned and then evaluate the particle velocities, which naturally will be different from what you estimate through the linear wave theory. How much is going to be the deviation? It depends on how much is your crest steeper than the trough. So, here is the horizontal water particle displacement, vertical particle displacement and the mass transport velocity. All these things we have seen in the small amplitude wave theory with examples, worked out examples. Is that clear? And this gives the expression for the subsurface pressure. All these variables are known to you, like K is the wave number, D is the water depth, Z is the point of defining the particle velocities, and then sigma is 2 pi by T, angular frequency. So once you have these expressions, so what you need to know is why you use higher order theories. What happens if you do not use higher order theories at situations for the conditions for which you are supposed to use higher order theories. That I have already illustrated with the example, that is very important. Now how to use, it is quite straightforward, because all these variables are already known to you. Only thing is the expressions are quite long. Is that clear? So relationship for particle velocities and the waveforms become complex as the number of terms retained increases. So usually they use fifth order theory. Once you have everything programmed, it becomes very simple. Is that clear? So the use of digital computers has enabled rapid solutions to obtain for higher order solutions. So usually fifth order theory is frequently used in estimating wave forces on structures, since many experimental constants derived from field measurements have been correlated with this theory. What does that mean? See, as I said, anyway, this pertains to the wave forces on structures. When we talk about the experimental constants, some of the have two coefficients mainly, which are called as the hydrodynamic coefficients of drag and inertia. These are derived only from experiments or from field. So you generate a wave, measure the force, and then from the force and the wave time history there is a possibility or a method to get the Cm and Cd. Cm and Cd are then given as a function of Keeling-Carpenter number. Refer to my lecture on wave loads on structures. Now you see that these coefficients, where are you getting it from? You are getting it from measurements either in the lab or in the field. So it is always, and these waves are not going to be sinusoidal, at least the lab you can try to generate sinusoidal. So that is the reason why they use the fifth order theory. The expressions of all these theories is given in appendix A, that will come as a part of the lecture. Comparison between the wave theories, comparison of between the wave theories and lab measurements as shown in example demonstrates the wide divergence of the results which can arise from various assumptions made in the different theories. I just simply highlighted that there is going to be some difference, but we will see what is the kind of difference we have. So this is a comparison between profiles, surface profiles, as given by Professor Dean in 1965. So you see the experimental profile is the thick line here, the second order Stokes line is here, then stream function theory is here, then you see the Airy's theory here. Okay. So you look at the kind of variation, and remember that this is for a given wave height, wave period, etc. So all this data are given here. So this is from the distance from the crest. Okay. So the deviation is quite large somewhere near the crest, and this is what really matters. So this explains why higher order theories or finite amplitude theories are needed. Yet another comparison, here you compare the comparison of profiles are presented again by Dean. The maximum velocities at each elevation. So at each elevation in the sense So, you have a time history here, you take only the maximum velocity and that is represented here. So, next you have this and you take only the maximum velocity and that is measured. So, it is plotted along the depth. So, some of the other theories are also included herein, like second order sinusoidal theory, which I am not going to cover here, but you see the solitary wave theory, sinusoidal wave theory, Airy's theory, all these things how it really differs. The variation is as from something like around 0.3 and it goes up to about 1.3, and the deviation is significant near the free surface. So, look at this variation, simple variation between the difference between a second order profile and the Airy's theory. Okay. That explains something about that has given us a brief description about the finite amplitude theories. Now, we move on to solitary wave theory. Solitary wave theory, as I said earlier, there are some researchers who are of the opinion that solitary wave theory, the solitary wave, I mean the tsunami can be, the characteristics of the tsunami can be represented approximately as that of a solitary wave, but there is another set of researchers who differ from this. In very shallow waters, wave crests become peaked and trough flattened, the surface profile is entirely above the still water line in the case of a solitary wave. So, the wave is therefore not periodic and has no definite wavelength. This is the major difference between solitary wave and other waves. Bushnell derived characteristics of the solitary waves in shallow water directly from general equation of a steady flow for a steady flow, and the derivation was quite straightforward. Solitary wave has proved useful in engineering problems such as study of very long waves like tsunamis, and in determining wave properties near breaking in shallow water, and for study of waves of maximum steepness in deep waters. Under such conditions, the wave characteristics are independent of wavelength and T and will depends only on H. In this case, the celerity, the speed of a solitary wave is given as root of, which we will see later. The profile given by, represented by the solitary wave can be represented as shown here. This is secant H, and here all other parameters known to you, x is being the origin at the crest. Based on this only you can draw the profile. Is that clear? Different values for a given C, given characteristics of H and D, use this expressions and traverse the profile from x. X is assumed, x is starting from the crest of the profile, crest of the solitary wave. The horizontal and vertical particle velocities are given by this expression where c is celerity as discussed earlier, and m and n are values or functions which can be obtained from a figure which is represented as a function of h by d, which will be shown soon. All other parameters are known to you because x is starting from the crest of the wave as said earlier. D is the water depth, S is below the still water line, M and N are obtained from the figure as shown here. Once you have H by D for the given wave conditions, you can derive the values for M and N, use that expression, earlier expression, to get U and W. So U max will occur when X and T equal to 0, and that is given as as shown here. The total energy in a solitary wave is about evenly divided between the kinetic energy and the potential energy. I will not go into the details of deriving the kinetic energy, although it is quite straightforward. Again, use the same principle as we have done for almost similar procedure what we have done for linear waves, and you see that the total energy can be obtained per unit crest width is given as this by this expression, whereas the pressure is given by this expression. So considering steady flow case where the waveform remains solitary and wave enters with the velocity v1 equal to Vc, v1 equal to c, v1 equal to c, then you consider these two locations. So this is d2 and this is d1, and here v1 is equal to c. Use the continuity equation as shown here, and then continuity equation is like apply the Bernoulli equation as given here, and then use the continuity equation, from which and rearranging v1 equal to v equal to c, you can obtain an expression as shown here. But then d1 equal to d1, and whereas d2 is going to be d1 plus this height of the wave. So substitute in this equation, then you get an expression for the speed of the wave, speed of the solitary wave. The speed of the solitary wave is nothing but the shallow water wave condition multiplied by this value, you understood. So if h is large, then this component is going to be higher, then you consider just a linear theory propagating in a shallow water, you understood. So when h becomes small with respect to depth, the limit, as I have told, for extremely shallow waters you can also assume it as equal to root of g into d plus h. So that is about solitary wave theory. Then we move on to the sinusoidal waves, wherein the sinusoidal wave, it was first described by Korteweg and De Vries in 1895, applicable over a wide range, that is d by L ranging between 1 by 10 and 150. But however, both Stokesian wave theory and the solitary wave theory are valid over a portion of this same range, as we have seen earlier. So sinusoidal wave theory is valid for the Husserl's parameter greater than 26. In our department, in the Department of Ocean Engineering, our wave maker can generate solitary wave theory, solitary waves as well as sinusoidal waves, leave alone other waves, because other waves any normal wave maker can generate. Knowingly or unknowingly you may be generating higher order wave theories. It may be difficult for you to generate a linear wave theory, linear wave. Whatever you generate in the lab, you assume it as linear wave, which is not the case, okay. So unknowingly what I am trying to say is, when you want to, you normally fix your wave height and wave period, you do not even bother whether which theory it is going to follow. But in the case of sinusoidal and solitary, when you want to use a wave maker to generate such waves, all these informations are built in, all these conditions are satisfied, only after which you will see that such kind of waves are generated in the flume. So the profile looks something like this. It has a very flat trough and a steep crest, a photograph of which was already shown to you. As wavelength becomes long and approaches infinity, sinusoidal theory reduces reduces to the solitary wave theory. As the ratio of wave height to water depth becomes small, infinitized wave, the wave profile approaches the sinusoidal wave profile predicted by the linear theory. These are all some of the statements. Then wave characteristics are described by what is called as modulus k of elliptical integral. So the profile is measured from the bottom seabed, and this is the profile. This is the water surface, the wave profile, and this is given by yt. Yt is the distance from the bottom to the trough, and Cn is the elliptical cosine mathematical function, and then k is complete elliptical integral of the first kind. K is k of k is a complete elliptical integral of first kind, then k is the modulus of elliptical integrals. As the argument, C of n square is often denoted simply by this, okay, as you can see here. The elliptical cosine function is periodic, where Cn is shown as shown here, it is periodic in space and time. So the modulus k, small k, as we have seen, is defined over a range between 0 and 1, and when k is equal to small k is equal to 0, the wave profile becomes linear, the sinusoidal, and when k is equal to 1, the wave profile becomes that of a solitary wave. The distance from the bottom to the wave trough yt, this can be obtained by this expression as shown here. For details refer, I would suggest for this to refer Coastal Engineering Manual. So the L is calculated as shown here, and these parameters have already been explained, and the wave period can be given like this. The pressure is provided by this expression, and as I have suggested, including the characteristics of the waves, refer Coastal Engineering Manual, or even the book from Ippen is also quite good. So that explains the salient features of sinusoidal wave theory. Then we move on to stream function theory. Although the Stokes waves satisfy the basic Laplace equation and the seabed bottom boundary condition, the free surface boundary condition is not fully satisfied. The free surface boundary condition I have already explained to you. The components of flow at the surface are not necessarily in accordance with the shape of the surface and its motion, nor is a restriction placed on the pressure immediately below the surface. The dynamic free surface condition in this case is provided like this, and the stream function solution may be expressed as given by this expression, equation 28, and evaluating by setting z equal to eta, not z equal to 0, to give a surface as shown here. This is the surface of a stream function that can be described by stream function theory. For a particular water depth, wave height and wave period, the function exactly satisfies the Laplace equation, the seabed, and the surface flow boundary conditions for arbitrary values of L, phi n, that is and capital Xn. So these values can be obtained numerically, so that the dynamic free surface boundary condition can be obtained as published by Dean. So I would not go into the details of the stream function theory because it is not that widely used, but still people, there are some cases where you need to know the stream function theory, and this is the series of references that I have collected, and there may be some recent literature also, but for a class like this I think it is good you look at some of these references in order to brush up and then go further into your research activity. Okay. Now let us continue with a few worked out examples. So for the sinusoidal wave theory I will show how the celerity is calculated. A wave travelling in a water depth of 3 meters and wave period 15 seconds and height 1 meter, find using sinusoidal theory, find wavelength and compare this with the wavelength determined by Airy's theory. Determine celerity, compare this with the celerity of the Airy's theory, determine the distance between the above the bottom of the crest Yc and trough Yt and determine the wave profile. This is the problem that we need to look into. So these pictures are given available in the coastal engineering manual or the shore protection manual. So for the given problem d is this much t, so you calculate the value h by d which is coming to this much, also calculate this parameter t divided by g by d which is working out to 27 point something. So get into this picture which shows the determination of square of modulus of complete elliptical integral. So this becomes handy, these nomograms. So get into this picture and get the value of k, and we get k as shown here 1 minus 10 to the power minus 5.51 or 5.1. So this shows the relationship between this k square which you have determined from the earlier plot to get you to the value for L by L square, that is nothing but the Ursell's parameter, and Ursell's parameter is working out to 290. Naturally it is greater than 26, so it is following sinusoidal wave theory. So once that is known, once this is known, this L square h divided by d cubed, you can arrive at the wavelength, and once wavelength, so this is the wavelength, and from the linear theory I do not want to explain to you how the linear theory is calculated, and from the linear theory you can calculate this as 80.6. So that is the kind of difference you have between the wavelengths. Okay. To check the validity of linear theory is already done. So d by L and this one I have already explained about the Ursell parameter, I need not have to go into that. So once you have calculated your L, it is quite straightforward to calculate the corresponding celerities. So in this particular case there is not much of difference between the celerities, and thus if it is assumed that the wave period is the same for both sinusoidal, and we can say that it is equal to 1, but that is not correct. Okay, there is still a difference between the sinusoidal and this one. The last one is about the percentage of crest and trough. So you have already selected this, and then you have to go and find out this value. So this is Yc, the portion of the location of the crest. So in this particular picture I forgot to tell you that you need to consider this h by d while selecting this point. Okay. So h by d here is 0.3 and 0.3 is somewhere here. So from this picture you can arrive at Yc and Yt. So we will move on to the second example. A wave height is given as 1 meter, wavelength is given as 60 meters. It is propagating, the wave is propagating in a water depth of 6 meters. Which theory could be adopted for the evaluation of water particle kinematics. For the wave with the same frequency, find the range of wave heights in which the stream function theory could be adopted. Take care of the breaking criteria. So the problem is quite simple, only you use this, the problem looks as if it is complicated, it is a very simple problem. The only thing is this is a kind of an exercise to make yourself familiar with this graph, that is all, which very often students forget. So wave height is given, wave water depth is given, so you calculate your d by L, corresponding d by L naught, okay, all these things are known to you. H by d t square also can be calculated. So for this picture you need h by gt square and d by gt square. So since wavelength is given to you normally, which is not the case, normally they give directly the wave period, but in this problem you are given wavelength, so you use the dispersion relationship and then you get the wave period. So you calculate the wavelength and then calculate your wave period and then you get these two pictures, and then for the stream function theory this one should lie between 0.17 and 0.017 and 0.006. Unfortunately this picture is not so clear, so you have to take the corresponding this value and the corresponding this, and then using these values for the stream function theory. So in this case for these two parameters Airy's theory is valid using this picture, okay. For stream function HD should be lying in between this value, that is h by, so the stream function theory is somewhere here, this is the region where the stream function theory too should follow the values. So using this limits h will be ranging between 4 and 11 meters, but you know that the maximum wave height cannot be greater than the wave height cannot be greater than 0.78 times water depth. That means here water depth is 6 meters, so the water depth, the wave height cannot be greater than 4.68 meters. So the range of wave heights that could be there is between 4 meters and 4.68 meters. Is that clear? So this is just an example to show you how you can use this. Unfortunately the picture is not so clear because it is quite a big picture, so you need to do this and probably use the handouts in case you want to understand better. Given water depth, find the ranges of wave heights, in which case stream function theory is applicable, Stokes is applicable, and which order. So you take a wave period in intervals of 1 second and tabulate the results. Remember again the wave breaks. So what we have done is, so here I have given the, on the first column I have given the wave heights, wave periods in intervals of 1, calculated the values of d by gt square, calculated the values of h by gt square, and then the range taking into considering the breaking criteria, and then range of wave heights. So this is not applicable because the wave is going to break. Then the range of wave heights that could be possible for the stream function theory. Is that clear? So use that picture, earlier problem we had that small nomogram, that nomogram need to be used here, okay. So up to 15 seconds we have given the variation of wave heights, and similarly Stokes wave theory I have worked out for the different starting from second, third, fourth order theory, calculated the h by gt square, this also is calculated, this calculated, then enter into the picture and enter into the nomogram and get the values of the wave height, the range of wave height that could possibly cover the different Stokes area waves. So with this I think we have completed the finite amplitude wave theories. So I hope this would be useful to you as a beginning, so that based on this kind of information you can just proceed further by reading additional books. Okay.